Bismillahirrahmanirrahim. My name is Kainat Abbasi. My roll number is 16TE83. This is the week 14 of digital signal processing, lecture number A. In this lecture, we will see about infinite impulse response filter design. An IIR filter, infinite impulse response filter, is described using the difference equation, that is y of n is b0 x of n plus b1 x of n minus 1, and then bm x of n minus 1 minus a1 y of n minus 1 minus an y of n minus 1. And we can write the transfer function of the above IIR filter by applying the z transform. H of z is equal to yz or xz, and we will obtain b0 plus b1 z inverse plus bm z raised to power minus m, and in the denominator 1 plus a1 z inverse and so on en z raised to power minus n. Let's see an example about infinite impulse response filter design. We are given a transfer function that is y of n is equal to 0.2 x of n plus 0.4 x of n minus 1 plus 0.5 y of n minus 1, and we want to find the transfer function. We will apply the z transform on the above difference equation, and will obtain y of z plus 0.2 x of z plus 0.4 x of z z inverse plus 0.5 y of z z raised to power minus 1, and the transfer function is y of z over x of z is 0.2 plus 0.4 z inverse 1 minus 0.5 z inverse. Non-zero coefficients. In the numerator we have b0 is 0.2, b1 is 0.4, then a1 is minus 0.5, and we want to find the impulse response. For the impulse response, we will write this separately as 0.2 divided by 1 minus 0.5 z inverse plus 0.4 z inverse 1 minus 0.5 z raised to power minus 1. We will apply inverse z transform. You can find this in the table given in the book, and the result is impulse response is h of n is equal to 0.2 0.5 whole raised to power n u of n plus 0.4 into 0.5 n minus 1 u of n minus 1, and by putting the values from 0 to infinity we can find the impulse response. This is infinite filter as the name shows, so the impulse response goes towards infinity. Then the next topic is bilinear transformation design method. The design procedure for BLT is as follow. Number one step, pre-wrap the given digital frequencies into analog frequencies. लो पास एंड हाई पास फिल्टर के लिए हम ये वाला फार्मूला यूज़ करते हैं, W of A is equal to 2 by T tan of omega dt by 2, and for band pass and stop filter we have omega AL, that is lower analog frequency 2 by T tan of omega LT by 2, and omega AH high analog frequency. Omega naught is calculated using this equation, and bandwidth is calculated using this equation. In the second step, we perform prototype transformation using low pass prototype. From low pass to low pass, we replace S by S over omega A. From low pass to high pass, we have S is equal to omega A by S. Similarly, low pass to band pass, S is equal to S squared plus omega naught squared S W. W is bandwidth. And from low pass to band stop, we have S is equal to SW into S square plus omega naught square. Then in the final step, substitute BLT to obtain digital filter. In this step, we will replace S by S is equal to 2 by T Z minus 1 Z plus 1, and we will obtain a digital filter. Let's see the example. We are given a low pass filter with cutoff frequency 1 radian per second. HP of S is 1 over S plus 1. Or we have to design digital infinite impulse response low pass filter with cutoff frequency 15 Hz and sampling rate 90 Hz. First we will find digital frequencies. Omega d is 2 pi f, that is 2 pi into 15, and we will find the time period, that is 1 over 90, inverse of sampling rate. Then follow the design procedure. First, number one step is pre-wrapped analog frequency using a low pass filter formula, and it comes out to be 103.92 radian per second. Then prototype transformation from low pass to low pass will replace S is equal to S by omega A, and omega A is 103.92, and it comes out to be 103.92 divided by s plus 103.92. Then apply bilinear transformation in which s is replaced by 2 by t z minus 1 over z plus 1, and after the calculations the final digital filter comes out to be this. Thank you very much.